right, we're heading back to do 16.4, which we temporarily skipped earlier in the semester. So we're going to be working in two space now. So we're going to have D as a simply connected plane region. So remember, simply connected just means there are no holes in it. Okay. C is going to be the boundary of D. Okay. Now, anytime you have the boundary of any region, by definition of it being the boundary, it's got to be closed. Because if I have a curve and it's open-ended, that's not the boundary of anything because stuff could leak out. It doesn't fully enclose it. We are going to require that this be a simple curve, which remember means that it can only intersect itself at the starting and ending point. So it forms a loop, but it doesn't intersect itself anywhere in the middle. So we're not looking at something like this. Okay. We're going to require that it be piecewise smooth, and we're going to require that it be oriented counterclockwise. Notice that makes sense for anything that's a simple closed curve because it's just a loop. It might be a loop that's sort of morphed and, going all over the place, but I can still talk about what it means to go counterclockwise around this, whereas with the figure 8, it's a little bit harder to do that. So that the fact that we can orient it counterclockwise is kind of linked to the fact that we're requiring it to be a simple closed curve. Okay. Then we're going to have a vector field F with component functions P and Q. We're going to require that that be continuous and have continuous first partials on some open region containing D. So basically, on the region that we're working on and nearby. It's got to be continuous with continuous first partials. Okay. So all of this is basically saying that everything has to be sufficiently nice. If I have a sufficiently nice region with a sufficiently nice boundary and a sufficiently nice function, then Green's theorem is going to apply. All of these niceness conditions are important. What I'm holding you responsible for remembering is the relationship between D and C. That C is the boundary of D oriented counterclockwise. And then what Green's theorem says is that if I wanted to do this work integral, or now I know if F happens to be velocity, I could think of this as a circulation integral. If I wanted to evaluate this, I can instead do this double integral over D, which is the enclosed region. Okay. So that looks somewhat similar to Stokes' theorem. Stokes' theorem would be for a work integral where my vector field was in 3 space. And in Stokes' theorem, we don't get this. We're getting curl of F dotted with N. Now, if I've got a vector field in 2 space, its curl isn't defined. But what I'm going to do is I'm going to actually prove Green's theorem by embedding everything in 3 space. So I've got in the xy plane, I've got my curve C and my enclosed region D. So here's D, here's my curve C oriented counterclockwise. I'm going to embed that in 3 space. Remember, this arrow with a little hook means that we're embedding things. So what that's going to do is that's going to just draw this region D, but now on the xy plane. So that if there was a point here, xy, in 2 space, that's going to map to a point xy 0 in 3 space. Okay. So I'm just viewing sort of the xy plane as being the xy plane in 3 space. So if I had parametrized my curve here, now if I've called that D, I can't actually call this region D because it's not actually the same region. This was points in 2 space, this is points in 3 space. I'm going to call this D tilde. You can call it whatever you want except D. It's not the same region. And it's just careless to use the same name. And unfortunately, your book doesn't set a very good example of this. It sort of embeds things freely in 3 space and uses the same name as we were using in 2 space. We're going to be more careful than that. Okay? If I had my boundary curve C and it was parameterized as R of T, where A is less than or equal to T is less than or equal to B, now I'm going to have my boundary curve C tilde, which can be parameterized as r tilde of t. Now if r of t was x of t, y of t, r tilde is just going to be x of t, y of t, 0. A less than or equal to t, less than or equal to b. So I'm embedding things in 3 space. I've got f, which was my vector field, which is just the functions, has component functions p and q. I can embed that into 3 space. I'm going to get f tilde, which will be a vector field with 3 components, p and q, which happen to just be functions of x and y. Z just won't show up in their formulas. And then 0 here. So any points I have, I simply attach a z value of 0. Any functions I have, I add a third component function of 0. And that's my embedding. Now once I have that, I now have that c tilde is the boundary of d tilde, and so I can apply Stokes' theorem to that. So here's essentially what we're going to say. The integral along c of f dotted with t ds is going to be exactly the same as the integral along c tilde of f tilde dotted with t ds. Moving things to say, I'm going to look at this as being on the xy plane in 3 space, as opposed to just on the xy plane, isn't going to change the value of this integral. It just puts it in a space where now curl is defined and Stokes' theorem applies. So I can say by Stokes' theorem, this is going to be the double integral over d tilde of curl of f tilde dotted with n d big S. Notice I don't need to put tildes over the t's and the n's. It's understood that t is tangent to whatever curve I have here. So this t is necessarily tangent to c. This t is necessarily tangent to c tilde. T just means the unit tangent vector to the curve we are working with. Similar, this means the normal vector to the surface that we're working with. Now, D didn't really have a normal vector because we were working with a region in 2 space. There is nothing that's normal to a region in 2 space because to have something normal to the xy plane would require me to leave the xy plane. But once I'm in 3 space, I can say, oh yeah, okay, so if d tilde lies in the xy plane, that's kind of nice because that means that the normal vector is going to be constant. And I know that the unit normal vector to the xy plane would have to point either straight up or straight down. Let's see which it does. We said that we were going to have our c, and therefore our c tilde, oriented counterclockwise. Now in 2 space, counterclockwise makes sense. In 3 space, I have to specify a perspective. But if I'm looking at the xy plane and talking counterclockwise, I'm talking about looking down on it. So looking from above, we're going counterclockwise. The normal vector is going to be pointing straight up. Okay. So this unit normal vector is just going to be 0, 0, 1, pointing straight up. Okay, so let's calculate the curl of f tilde. So that's the del operator crossed with f tilde. That's going to be the symbolic determinant I, j, k, partial x, partial y, partial z, p, q, 0. And just a reminder, p and q are the same component functions we had in our original vector field f, so they are functions of just x and y. There are no z's in them. Okay. So when I go to calculate this, my first component, I'm going to get the partial of 0 is just 0, minus the partial of q with respect to z, that's going to be 0 because there are no z's in the formula for q. If I look at the j's, partial of p with respect to z is 0 for the same reason. There are no z's in that formula. And then minus the partial derivative of 0 with respect to anything is going to be 0. And then if I take a look at the k component, that's going to be the partial of q with respect to x minus the partial of p with respect to y. So, let's see. Now, I can plug in to this integral. I can say we're getting the double integral over d tilde of the curl of f is just 0, 0, partial of q with respect to x minus the partial of p with respect to y, dotted with 0, 0, 1 ds, viewing that still as a surface integral. So that's the double integral over d tilde of, I'm going to get nothing, nothing, and then I'm getting one copy of the partial of q with respect to x minus the partial of p with respect to y ds. Now, this is still a surface integral in 3 space, so what I want to do is take this surface that's part of the xy plane, whose equation is z equals 0. So I can view that as z being a function of x and y. Okay. So if I project d tilde onto the xy plane, I'm going to get d, because it's just sitting there on the xy plane. So that's just going to be d, partial q, partial x, minus partial p, partial y. Okay. There were no z's in this formula, so if I'm using as my parameterization that z is a function of x and y, and it's just the 0 function, there's no place for me to plug in 0 for z here. So I've just got a function of x and y here. And then ordinarily I would get some scaling factor that would allow me to switch to dA, but that scaling factor is actually just going to be 1. Because if I've got this region that's sitting on the xy plane, so I project it onto the xy plane and I get essentially that same region, just viewed now as a region in 2 space, I have not stretched or shrunk the area at all. So the scaling factor will just be 1. We can also see that because we had said that our unit normal vector was n equals 0, 0, 1, but that's also the non-normalized normal vector I would get if I had wanted to, at this point, switch to integrating with respect to d. Because I know I would have a 1 here, and then what I would have here would be the opposite of the partial of z with respect to x, and the opposite of the partial of z with respect to y, but both of those would just be zeros, because the formula for z is a constant formula. There are no x's or y's in there. So if I wanted to, at this point, I could have said, instead of this being n, I could have said this is the non-normalized normal vector, and I could have gone right to integrating over d with respect to area in the plane. And that's exactly what Green's theorem states, that we can integrate this difference of these two partials. Now, that's not the curl of f, that's the curl of f tilde dotted with the unit normal vector 0, 0, 1. Okay. But I can sort of remember that, so I don't have to, in order to use Green's theorem, I don't have to work through this proof every time. But I know I'm horrible at remembering what order subtraction problems come in. And I'm horrible at remembering, well, which function am I taking the derivative with respect to x of, and which am I taking the derivative with respect to y of? If I remember where that comes from, that it comes from just embedding things in 3 space, I can work it out fairly quickly. In fact, if I remember that it's just going to be the k component, I can remember that it's actually just going to be the determinant of this 2 by 2 matrix. That's what my integrand is. That's not a full-on proof, but that's a nice mnemonic device, that my integrand will simply be the determinant of this 2 by 2 matrix, which happens to be the k component of the curl of f tilde, if I were to embed this in 3 space.